Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing various other topics. Last topic, the theory of acids and bases, is completed last time, and today we are going to start with new topic, new chapter, that is coordination chemistry. This coordination chemistry is important because it is one of the most important branch of chemistry which deals with variety of fields where it can be applied, and this is also of greater theoretical interest. The coordination compounds are applicable in catalysis, synthetic organic chemistry, or various other fields such as dyes, etc. Today we will see here the introductory part and history of the coordination chemistry. So here we will see the first point, that is introduction and history. So these are our today's points of discussion. First of all, we will see what is the coordination chemistry. So coordination chemistry is a chemistry of compounds in which a metal ion is present at the center and it is surrounded by a specific set of ligands, or we can say, in other words, instead of ligands we can say the species, means molecules or ions of any suitable type and in specific number. For example, we can consider, say this is Ag, NH3 twice plus 1. So this is ionic species because it carries one positive charge, and you will find that this silver ion is bonded or surrounded by two ammonia molecules, and such type of species is called coordination compound. And the part of chemistry which deals with the structure, synthesis, applications of such compounds is called coordination chemistry. Here the part of this means this is the coordination compound contains a metal ion and it is bonded to ammonia molecules. We can split this structure in this way. So silver is at the center and these are two ammonia molecules attached with this. We know that silver is monovalent ion, but it is bonded to two ammonia molecules. So this is a coordination compound. So we will discuss why this is so in later part when we discuss the structure. The next point is, what is a ligand? So we can see, we have discussed here that here in case of Ag, NH3 twice, Ag, NH3 twice plus 1. So here silver ion is Levy's acid. This is Levy's base. So formation of such compound, coordination compound, is the reaction between a Levy's acid and Levy's base. So silver ion has +1 charge. These NH3 are neutral. So the resultant charge on the species is also +1. plus 1. And you will find that the Lewis acids are metal ions and Lewis bases are either neutral or ionic species. So here we have example of ammonia, which is a neutral species. Similarly, we can have H2O, which is also neutral. Then we can have other neutral molecules of various types, or we can have some ionic species such as halides, Cl minus, Br minus, I minus, OH minus, etc. So all these species are called ligands. So they are called also ligands. Means ligands are the species which are bonded or which can form covalent or coordinate type of bond with metal ion and form a complex species is called ligand. Then what is a coordination compound? We'll see what is the coordination compound. So coordination compound is a neutral species in which the coordination compound can be a single species or it can be a pair of cation and anions, in which at least one of the ion is a complex species. Then only we can say it is a coordination compound. Sometimes we can have both cations and anions of complex nature, like this species. So here you find that AgNH3 twice plus is a complex cation. Similarly, we can have complex anion like this. Fe CN6 3 minus is complex anion. So this charge can be neutralized by using here K3. So we can say this compound is K3FeCl6. Now the 3 minus is neutralized. So this becomes potassium ferricyanide. So in this way we can have such number of examples which are obtained by using transition metals, especially transition metals. Here you will say that the complexes can be whether they are obtained from the simple representative molecules or p block elements, but this is not so. Only the transition metals can give such type of complexes or coordination compounds, in which we can have such type of examples. So we have seen here a few examples. Now we will see that these species are having the structure like this. For example, we see, okay, we take this example, CO, Cl3, 6 NH3. So here you will find that cobalt is at the center, then there are these NH3, 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 NH3 surrounding the middle like this, NH3. And this species, here cobalt is in 3 plus state, so it will carry 3 plus charges, and these are further neutralized by 3 Cl minus. So we have this formula COCl3 6 NH3. So in such complex compounds or coordination compounds, metal ion is at the center and it is surrounded by a specific set of ligands. So here are 6 ligands. The number of ligands can be 2, 3, 4, 5, 6, etc. So it depends upon the metal and its oxidation state. Further, the size of the metal ion also matters. The size of the ligands also matters, etc. Then, if we see the history of coordination compounds. History. So we have seen here this part, that is what is coordination chemistry. Now we will see this, what is history of coordination compounds. If we see the period of ancient years, then we find that the scientists, or there were various artists who were using variety of colors, and it was found that these artistic dyes or colors are composed of coordination compounds. But they did not know that these are actually coordination compounds, but they were using such compounds which were obtained in laboratory by specific procedure. So since these compounds means complexes of these transition metals, maximum complexes are colored in nature, they are mainly used for dyes or color or for artistic purpose, artistic applications. Then these dyes, or we can say pigments, which were used for artistic purpose, as we have seen that they were used till late 19th century. But they did not know that these compounds were the coordination compounds. Later on, it was found that the colors or dyes which were used by artists, for example, it was a Prussian blue, the dye named by the artists was Prussian blue. So this is the Prussian blue. So this dye is formulated as K Fe. Here Fe3 is oxidation state of Fe, and into square bracket it is shown as another Fe with oxidation state 2. Then in small bracket it is Cn, cyano 6. The number of such Cn minus is 6. So the formula is K Fe into square bracket Fe Cn6. But the difference is that this K outside the square bracket is in plus 3 oxidation state, and inside the square bracket it is in 2 plus state. So this Fe is at the center. So if we see the structure, you will find that this Fe in the 2 plus state is at the center. And the Cn minus are attached like this. Cn is attached like this. And further, these Cns are further attached to Fe in 3 plus state. Fe in 3 plus state, like this. So we can show here Fe in the 3 plus state. So we can get the structure in this way. So this is our Prussian blue. Now, if we see the history again, it shows that this Prussian blue is discovered, or we can say invented in 1704 by Dispatch, the scientist Dispatch. It was used as a dye for uniforms, coloring the uniforms of Prussian army, and therefore the name carries Prussian blue, and it was deep blue colored. Hence the name appears as Prussian blue because it is deep blue colored, and it was first used by Prussian army. Then this dye was later on used extensively, widely by various other artists till late 19th century, 18th century and early 19th century. It was also used in cyanotype photography, blueprints, and for dyeing blue jeans, that is jeans with blue color. Then another color was obtained here. So this is Prussian blue. This is Prussian blue. Then second is bright yellow dye. This is bright yellow dye. So this bright yellow dye is also named as orline, or it is cobalty yellow. Orline or cobalty yellow. It is used since 1831, and it has formula K3CONO2 This is hydrogenate form. So here in this coordination compound, metal and cobalt is at the center, and nitro groups and O2 groups are arranged octahedrally around the cobalt atom. The charge on this species is neutralized, means because of 6NO2 minus, the charge, negative charge is 6. Ordinary cobalt neutralizes 3 of these negative charges, and remaining 3 charges are neutralized by 3K plus. So the formula is K3CONO2. So it was used as a pigment since 1831. Then next is alizarin red. Next is alizarin red dye. Then this alizarin red is also aluminium lake dye. It was obtained from the roots of madder plant. It was extracted from the roots of madder plant. It was used by peoples from various countries like Persia, Egypt, Greek, Roman, French, British, etc. Especially British and French army used these dye for coloring their uniforms, army uniforms. And because of their red spots, it was also recognized specifically for the British army. It is also used in histology as a stain. Then, if we see the structure of this, it is like this. You can say this is calcium, is calcium with 2 plus charge. structure is like this. So this is the structure of our alizarin ring. Alizarin ring. You will find that here aluminium is at the center. It is hexacoordinated, means it is bonded with 6 coordinate bonds like this. Out of 2 are attached to this OH and OH2. H2. This is OH2 or H2 same. And 4 linkages are with these oxygens of this part. So this structure is called alizarin ring. So this alizarin ring is used in various areas where it was also used in stain biological purpose for as a stain. Then we will see what is the difference between coordination compound and other species. So you have seen that this is our coordination compound. Then if we see another example, that is, say this is AlOH4 minus. AlOH4 minus. This is also a coordination compound. But if we see that this, if we compare this with sulfur dioxide, sulfate group, SO4 2 minus. You will see that here metal is at the center and it is surrounded by 4 such species. Here aluminum is also metal, it is surrounded by various species. But here sulfur is at the center, which is not metal. So this is a non-metal main group element and it is surrounded by oxygen. So this is not coordination compound. So in this way we can have other examples such as PCl3, PCl5 or sulfur dioxide, etc. Then if we see the bond between this aluminium and oxygen or this aluminium and oxygen, this bond is electron pair and this electron pair is contributed by these oxygens which are electron rich species. They carry electron pair. Similarly here also oxygen also provides this pair completely for bonding between aluminium and oxygen. So the metal ligand bond pair is contributed by ligand and that is why it is a dative bond. Means it has directional characters like this: metal ligand bond. It has directional characters. The electron pair of ligand is pushed towards metal ion. So it is called a dative bond or coordinate bond, and this is also a covalent in nature. So it is called coordinate covalent bond. Further, if we see the theories which were proposed to explain the coordination compound or coordinate bonding, nature of bonding in such coordination compounds. The first theoretical approach was proposed by Graham in 1837. So he proposed his concept as the first theory, in which he said that if we take NH4 plus iron like this, if we take NH4 plus iron like this, and if we replace any of these hydrogen ion with a metal ion, then it gives a coordinate bond, and this can be considered as a coordination compound. So this was his theoretical approach, but it is not applicable to other compounds like these. So such compounds were not explained by him. So this theory failed earlier or at the earliest. Later on, another scientist in 1871, that is Blomstrand, he also extended this Graham's concept, in which he said that the ligands containing ammonia, here the nitrogen has, means according to him, the nitrogen has the lower valency -3 and higher valency is -5. So according to him, in such coordination compounds, the nitrogen present in ammonia, that is NH3 molecule, is pentavalent, and because of or using such pentavalency, the ammonia can form metal nitrogen bonds. 5 such bonds can be obtained, and with the help of this, he tried to explain the structure of some complexes like this. For example, COCl3 6NH3. He tried to explain this in this way. where he showed that this is cobalt metal. It has NH3Cl. Another here it is also NH3Cl, and in between there are NH3, 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 NH3 and Cl. So he proposed a chain-like structure in which you will find that each nitrogen is pentavalent. So he proposed this higher oxidation state, means higher valence of a central atom present in the ligands, and with the help of such structure he tried to propose his theory. He also proposed the use of such concept and forming catenation structure, catenation property in carbon also, where carbon uses its 4 valence plus 4 valence. Similarly, another scientist, that is Sophus Maris Jorgensen, extended this theory, extended this Graham's theory, and he also used this concept, that is formation of such chain-like structure, chain model we can see, where the pentavalent nitrogens are used. And according to him, the structure can be shown. He also supported this structure by reacting the, he synthesized a variety of such chloroamine complexes, such type of variety of complexes. Then he also tested these complexes for the presence of Cl- using AgNO3 in excess, and when he obtained the AgCl precipitate, he explained the concern of such precipitate with the number of Cl- present in the complex in the form of equivalent Cl- ions. So using these Cl-, he also succeeded to propose his concept in better way. So this concept or this model is also considered as Blomstrand-Jorgensen, and he prepared 4 such examples which are having different colors. And after this we will see the various structures here, and later on next scientist in 1893, that is Alfred Werner, he proposed his theory called Werner's theory. So that will be discussed in detail. Now we will see some examples which are used here to explain the Blomstrand-Jorgensen's concept, as well as it can be compared with the Werner's model. So we can compare this with Werner's model. We can show this, that is name or color, then Blomstrand, Jorgensen, chain formula. Then equivalent number of Cl-. Then Werner's formula and equivalent number of Cl- in the complex. So the complex were named in the beginning according to the color exhibited by them. So they are named as UTO first. UTO, or it is yellow or yellow. The formula of this was shown as like this: NH3Cl. The Cl, when tested, means when the complex was tested with AgNO3 in excess, it gave precipitate equivalent to 3Cl minus ions. So 3. The number of this is 3. I will show here. The equivalent structure proposed by Werner is like this. Cobalt is at the center. The NH3 are like this. Three plus, and these were neutralized by 3Cl minus. 3Cl minus, Cl minus, Cl minus, like. And this Werner also proved that the equivalent number of Cl minus are 3, and it was supported by the precipitate of AgCl. The next compound is our purium, and it is purple. It is having structure like this: CO, NH3Cl, NH3, 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 NH3Cl, and it is only Cl. So one of this NH3 is removed. Then this is equivalent to 2Cl minus. Like it has structure like this. Cobalt is at the center. So these are occupying the positions like this. So the charge on this complex is 2 minus. Here one of them NH3, that is out of 6, once NH3 is replaced by Cl minus. So the charge on the complex is 2 minus, and it is neutralized by the 2 plus, and it is neutralized by 2 Cl minus. Then the next compound is PreCO. Next compound is PreCO, and it is green in color. So it has structure like this. CO, Cl, Cl, then NH3, 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 NH3Cl. It is having the Cl minus equivalent to 1, and the structure is like this: CO, NH3, NH3, this Cl, Cl, NH3 NH3 plus 1, and it is neutralized by plus Cl minus 1. The number of Cl minus equivalent is 1. Then the last compound is Violio. It is violet in color and it has structure like this: CO, Cl, Cl, NH3, 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 Cl. It is having the Cl minus equivalent to 0 when tested with Ag and 3 indexes, and it has structure like this: CO, NH3, this is NH3, Cl, Cl, here it can be like this. So there is no charge and no Cl minus. So the Cl minus equivalent is 0. So according to Werner, the structural formula is like this. The equivalent number of Cl minus are like this, which is also similar, which is given by Jorgensen and Bronsted. But the structural representation is much different. And you will see that there is no geometrical approach here in these structures. But the geometrical approach shown by Werner gives greater stability and strength to the theoretical approach exhibited by Werner. So this is the greatest success. This success is much greater for Werner because the Lewis concept and as well as the discovery of electron had yet to be took place. So Werner also obtained the Nobel Prize in chemistry in 1931 because of his very important and revolutionary concept or theory. So with this we will stop our discussion and we will continue our next point, that is Werner's theory, in the next lecture. So till then, see you next time. Please subscribe to this channel, press bell icon and like button. So see you next time.